Today, we're going to try and solve a mystery. We're going to try and figure out how people make little LEDs blink. You may have seen tools or music boards or things like that have LEDs on them that flash and light up. And you might have wondered, well, how do they do that? Well, today, we're going to solve that mystery. In order to do that, we're going to have to learn about a couple different things. We're going to have to learn a little bit about schematics and components. We're going to have to learn a little bit about breadboards and a little bit about programming. Now, each of those topics could consume at least an entire class, if not an entire semester. So we're clearly not going to go into extensive detail on any one of those, but we're going to just give you a brief introduction to these so that you start to get familiar with some of the language and some of the ideas that we're going to be exploring more fully throughout the rest of the semester. Okay? So any questions before we get started? All right, cool. So, like I said, the goal for today is to make an LED blink like this. Okay? This is what you're going to do in lab, and we're going to go through together in class some of the things that will help you actually build this, okay? So, you need to have, if you're going to be building an electronic circuit, you almost always start with a schematic diagram. This is like a blueprint for a house. It tells the builders how to make the thing that they're building, okay? So, I will show you the schematic diagram to make an LED light up. And then we'll talk a little bit about what it is and what it means. So that's the schematic diagram to make an LED turn on. So you might notice that there's a bunch of symbols there and lines and stuff. So let's talk about what's actually going on there, what all these things mean, okay? And why we need them in order to make this LED turn on. The first thing I want to point out is this symbol over here. Anybody know what this symbol is? If not, that's totally fine, because you're brand new. This symbol is an LED. So if you want to make your own schematic diagram and you want to tell somebody to put an LED in a circuit, this is how you draw it. Okay? So let's talk a little bit about what LEDs are. Has anybody heard of an LED before? A few people. All right. So LEDs are little lights. LED stands for light emitting diode. And these are showing up all over the place now. They are found in car headlights. They are found in the overhead lighting that you have in your house. They're quickly replacing fluorescent and incandescent bulbs as the main source of light. And that's for a couple reasons. First of all, they are probably the most important thing is that they're very efficient. LEDs emit only one color of light. So they light up your house, and the light that comes out is just the light that you want. Incandescent bulbs are less efficient because they emit lots of different kinds of light, including heat. So when you screw in a light bulb, an old-fashioned light bulb, you are getting some light, but you're also getting a lot of heat in that room. That's not necessarily what you want. And that heat is energy that's being wasted. It's not being directed towards lighting the room. So LEDs are much more efficient. they can also be smaller than incandescent bulbs. So I've got a couple of examples of LEDs. I'll pass them around here. These are little tiny bulbs, and they work in a fundamentally different way than incandescent bulbs. Okay? Incandescent bulbs work by heating up a thin piece of wire and making it glow. But LEDs have a fundamentally different process inside that actually creates the light. Okay? So this is the symbol for an LED, and the name is light emitting diode. So you might ask, well, what is a diode, and why is this a light emitting one? A diode is a type of component that allows electricity to flow through it in only one direction. Okay? So a light emitting diode is a special type of diode that allows the electricity to flow through in one direction, but also creates light while it's doing that. Can you guys see this color? It's a little iffy. Let's try this. Is that better?
Yeah.
Yeah, okay. So the symbol for a diode is actually very similar to the symbol for an LED. So if you draw a symbol like this is a diode. If you add the little extra arrow that's supposed to look like light coming out, then it becomes an LED. Okay? So this is an LED symbol, this is a diode symbol. So any questions about LEDs? All right, so then let's work our way around the schematic diagram and see what else is going on. So we've got this LED symbol here, and then there are these lines. In a schematic diagram, the lines represent an electrical connection to other components. So you can think of them as wires, but really they are, and they could be wires, but they could be just connections in a printed circuit board, or they could be connections in a breadboard, which we'll see in a minute. So really the lines represent electrical connections. All right. So we've got an LED. What else do you think you might need in order to make an LED turn on and shine?
Power source.
Power source. Exactly. And that's what we have over here. This schematic symbol is a DC power source. It could be a battery, or it could be a power supply, but it represents an electrical power source. And typically, there will be some indication about what voltage is being supplied by that power source, along with the symbol. So in this case, we're showing a 9-volt supply. You could easily change that to 12 volts or 5 volts or whatever you want.
DC means power also?
DC stands for direct current. Yeah, and that is, we'll talk a little bit more about what that means later, but basically it means that the voltage doesn't change. There are two types of electricity. There's DC and there's AC. DC is just constant voltage. It always stays the same. AC is what comes out of the wall, and it varies over time. Sometimes it's positive, sometimes it's negative, and it goes back and forth very fast. So this is a DC power source. We're going to draw an AC power source. It would look like this. You've got a circle and a little sine wave in it, like that. So, in this case, we've got an LED that's going to turn on, and we've got a power source to give it energy, to make it turn on. But now, we've also got this other thing. Does anybody know what that is down there?
Resistor.
A resistor. Yeah, exactly. So let's talk about resistors for a minute, and then we can try and figure out why we might need them. So resistors are these little components that resist the flow of electricity. Basically, they make it more difficult for electricity to move through the circuit. So I brought along a couple of examples of resistors here. They come in different values. So some of them make it very, very difficult for the electricity to flow through. Some of them only make it slightly harder for the electricity to flow through. Okay? So I'll pass these around. You can see that they're all about the same size, and you can take a look at them more closely. So you might think that they all had about the same effect on the electricity. But actually, that's not true. This one is a 1 ohm resistor, so that means that it only provides a very small amount of resistance. And this one is a 22 million ohm resistance. So this one is 22 million times more difficult for the electricity to get through than this one. Okay? They're the same size, the same shape, same everything. The only difference on them, the only way that you can tell them apart is that there are different colored bands that indicate what resistance they are. So these little color bands tell you what the resistance is. We're not going to go into what the colors mean today, but we'll talk about that in a later lecture, and you'll learn how to actually read those color bands and figure out what they mean.
What about them makes them more resistant?
That's a great question. Basically, electricity is the movement of electrons, and this is getting a little bit ahead of ourselves, so you don't have to understand all this right now. But electricity is the movement of electrons. Basically, it's electrons jumping from one atom to the next, And certain materials make it easy for the electrons to move. So metals make it very easy for, they don't hold on to their electrons very well. So it's easy for electrons to kind of slide from one atom to the next. Other materials hold on to their atoms very tightly. So it's very hard for those electrons to jump from one atom to the next. So basically, in a resistor, you've got a mix of different materials. You've got some conductors that make it very easy for the electricity to move, and you've got some insulators that make it very hard for the electricity to move. So with the smaller resistors, the ones where it's easier for the electricity to get through, the mixture includes more of the conductors. With the bigger value resistors, where it's more difficult for the electricity to move, those include more of the insulator in the mix. So it's more of those atoms that hold on to their electrons. Does that make sense? Sort of. It doesn't have to be perfectly clear right now. We're just getting started, but that's in general what's going on. So let's get back to our mystery here. How do we make the LED blink? So we know that we've got an LED because we want to turn it on. We've got a power source to give it power, and now we've got a resistor in that circuit And we just talked about resistors a little bit. We said that they make it difficult for electricity to flow. Now, why would we want to make it difficult for electricity to flow through our circuit? I mean, we want the electricity to flow and turn on the LED, right? So why would we make it difficult?
So you don't waste.
Yeah, that's a good point. If we didn't have a resistor in there, then we'd be shoving a whole lot of electricity through here. And that might make the LED glow brighter, but it might also waste a lot of electricity. So if we were running off of a battery, it might run down our battery really fast. Okay? So that's definitely one thing. Another thing that might happen is that the LED might get really hot. Okay? LEDs are rated to handle a certain amount of electricity flowing through them. So there's a maximum amount of electricity that each LED can tolerate. If you put electricity through there up to the maximum value, then you're okay. But if you start pushing more than that through, you start to create heat, and the LED can become damaged. And in extreme cases, if you put way too much electricity through there, the LED can overheat, it can start smoking, and it can even explode in extreme cases. Okay? So when we have a resistor in a circuit like this, we call it a current limiting resistor, because it limits the amount of current that's flowing through the circuit, and that's intentional. We limit that current so that we don't damage the components, and so that we don't waste electricity, like you mentioned, like Ann mentioned. So does that make sense? Okay, cool. So we've talked a little bit about how or what circuit we would need to build in order to actually make an LED turn on. Now let's talk about how we can build that circuit. Okay? So what we've shown so far is that we need an LED, we need a power supply, we need a resistor, and we need them all to be connected together. But there's lots of different ways that you could make those connections, right? You could solder components together. You could put them into a breadboard or a printed circuit board that was specifically designed for this. You could kind of tie or wire wrap things together. So there's lots of different ways to make these connections, and all of them have certain advantages and disadvantages. When we're in the lab, we're looking for a way to make circuits that's quick and easy, and also that is reconfigurable. So you could make this circuit today, and then you could take everything apart and use the same components and make a different circuit tomorrow. Okay? So the thing that does that nicely is this thing called a breadboard. Okay? So let's talk a little bit about breadboards so that we can see how we can actually make all these connections that we need. Alright, so breadboards are little plastic boards that look generally like this. They're rectangular, they've got this trough running down the middle, and then they've got these rows of holes. Like this on both sides. And these breadboards are specifically designed to help us make connections between different components. Okay? So the way that they work is that underneath the breadboard, underneath the little holes, there are metal troughs. And these metal troughs make electrical connections between all of the holes in one row. So if you plug something into this hole right there, this hole, it is electrically connected to every other hole in that row. Okay? So if you plug something in there and then plug something in over here, the two things are electrically connected to each other. Okay? The same goes for the next row, and the next row down, and the next row down. So if we call this row 1, row 2, row 3, if I plug something into the leftmost hole in row 1, it's connected to the rightmost hole and every other hole in between. If I plug something into the middle hole in row 2, it's connected to all the other holes in row 2. Yeah?
But you couldn't connect something into row 1 and something into row 2. They wouldn't be connected to that.
Exactly. If I plugged a resistor in row 1 and an LED in row 2, they would not be connected to each other. Yeah? Yep. And there's no connection across this trough either. So the left side of the board is not connected to the right side of the board. Okay? So this would be like row 20 or something like that. So row 20 is separate from row 1, right? So those two things are not connected to each other. Does that make sense? Okay. So these holes are just the right size for the ends of the components, like the end of an LED or the end of a resistor. You can push the end of the component into that hole, and it should make a firm electrical connection, and then you can use that for prototyping. Okay? So that is the basics of how breadboards work. Okay. So now we've got this circuit diagram. We know which components need to be connected to each other. We've learned a little bit about breadboards, so we know how we can connect components to each other. So let's actually do it. Let's build this circuit. I'm gonna put on the overhead projector so that we can all watch what's going on, and then I'm gonna build the circuit with you. We'll go through the schematic diagram and try and actually put this thing together. Okay? Any questions before we get started? The projector always takes a minute to fire up, so please bear with me. Okay. So this is the breadboard that I was telling you about. You can see that there are the holes on the left, the holes on the right, and then this is the trough that runs down the middle. So this is sort of like our blank canvas. This is where we're going to start, and we're going to add the components that we need in order to make that circuit. So we can start with our LED. Now, LEDs are one-way devices, right? We said that they allow electricity to flow through in one direction, but not in the other direction. So that means that the orientation of the LED is very important. If you put it in one orientation, it'll allow the current to flow through, and it'll light up. If you put it in backwards, it will block the current from flowing through, and it will not light up. Okay? So we need to know which way is which. The way that you can tell, well, there are several ways that you can tell, but the surest way is by looking at the body or the dome that is on top of the LED, or the at the very base of that, there is a little skirt, kind of, and it is slightly flattened on one side. So it looks something like this. It's rounded on one side and it's flat on the other side. And if you were to compare that to the schematic diagram, the flat side of the LED corresponds to the side of the diagram that has the line on it. And there should be one leg that comes out of the flat side of the LED and the other leg that comes out on the round side. Okay, so this is the physical shape of the LED. This is the schematic diagram. And for reference, this is called the anode, and this is called the cathode. So we have to look at our LED and figure out which side is which. So I'm going to wade in here and see if we can see this. Okay, so can you see on the right-hand side there, the LED is slightly flat in the middle? Right. Can you guys see that? Yeah, so it's pretty subtle. When you're looking at it in real life, you have to look very carefully, but that's what's going on. Okay, so
And the flat side is where the electricity goes to.
well, the electricity is flowing through the device, so you just have to make sure that the flat side on the LED is lined up with the flat side on the diagram. Yeah. Okay. All right. So what I do when I am building a circuit is that I treat it sort of like a connect the dots problem, okay? So what I mean by that is that I find 2 points that are supposed to be connected, and then I just make that connection, okay? So in this case, I'm going to start out with the power supply. So this is the positive side of the power supply, and this is the negative side. So I'm going to look at the power supply, and I see that the positive side of the power supply has to be connected to the anode of the LED. Okay? So I'm going to look for those two things, and I'm going to make that connection. The positive side of the power supply is also known as VDD. The negative side is also known as VSS. Okay. So I know that VDD has to be connected to the anode of the LED. So I look over here on my board and I find that there's VDD labeled on the top of that board. Okay. And if you look closely, you can see that VDD is right next to these 5 black holes there. So what we're going to do is we're going to plug the anode of the LED into one of those 5 black holes. Okay? And then the cathode is just going to go to any place that you want on the breadboard, because we haven't connected that to anything yet. right? So we made our first connection. We've connected the anode of the LED to VDD. Any questions about that? Okay. So then we can make our next connection. We see that the cathode of the LED needs to be connected to one side of a 470 ohm resistor. So we said that the way that you can tell what value a resistance is by looking at the colors on the resistor. And we're not going to go into what all the colors mean right now, but we do need to know what a 470 ohm resistor looks like. So that one is a yellow, violet, and then brown. Okay, so we're looking for a resistor that has color bands on there that are yellow, violet, and brown. Now these colors are the bands are very small and the colors are kind of faded sometimes, so it's hard to see. You have to look very, very carefully in order to pick them out. But we can zoom in on this, and hopefully you can see what it's supposed to look like. There, so it's supposed to be yellow, violet, brown. And then there's a gold band on the right. We'll talk about that later. But the main colors are yellow, violet, and brown. Okay. All right, so we've got this resistor. And we're going to make a connection to the cathode of the LED, right? So remember, the cathode is this end, and we plug it into this hole in the breadboard, and that hole is connected to every other hole in this row. So if we plug this resistor into another hole in that row, now the resistor is connected to the cathode of the LED. You with me? Questions about that? Okay. Then the last thing that we're going to do is we see that the other side of the resistor gets connected to VSS. Okay? So we take this other side of the resistor and we plug it into one of these holes up here at the top that says VSS. Okay. So now we've made all of the connections that we need. We connected the power supply to the LED, the anode of the LED. We connected the cathode of the LED to the resistor, one side, and then the other side of the resistor over here to VSS. So we've made all the connections, so now our circuit should be ready to go. We can turn it on using this little switch down here at the bottom. There are 3 positions for this switch. 0 is off, 1 and 2 are on. So if we turn this switch over to position 1, sure enough, our LED turns on. Okay. So we made our first circuit. Pretty cool, huh? So you guys are going to get to do that. Like I said on Monday in our introduction, we really value hands-on learning. We want to get you guys going right away. So you guys are going to get to do this yourselves today. So you're going to build your very first circuit today. So that's going to be pretty cool. Okay. Now, we got the LED to turn on. Yeah?
What's the point in the resistor in this circuit? What does it do other than like limit electricity?
So,
do you need it?
Yeah, we do need it. This is a current limiting resistor. It limits the amount of electricity that goes through the LED so that we don't waste battery and also we don't damage the LED.
Okay.
Yeah. Other questions?
Could you lay out where the power starts for me? I kind of came in a little late. So like, it starts from the circuit board, goes to the LED, and then goes to the resistor, or is it backwards?
Yeah, so the power comes from the battery here, and in this case, what we're going to do is we're going to use these rechargeable batteries. Okay.
Okay.
So when you go into the lab, you're going to pick up a kit that has the Bobot in it and the circuit boards, and then you're also going to pick up a rechargeable battery separate. The batteries and the kits always stay separate. The kits go back together at the end of every class, and they go back in their box. But then the batteries go back in a separate box because they need to be recharged every night. So we always put the batteries back separately. So the power starts in the battery, and then you have to plug the battery into the circuit board here. So the batteries all have this little pigtail on the end of them, and you plug that in to the circuit board right up there on the top. Okay? So then this printed circuit board takes the power from the battery, and it routes it all over. It does different things with it. In particular, one of the things it does is that it connects it up to these little holes in the top that are labeled VDD. So the positive side of the battery is connected to these holes that are labeled VDD, and then the other side of the battery is connected to these holes that are labeled VSS. Okay. So that's how the power actually gets there.
So they're connected positive, negative, respectively.
Yes. Positive to VDD, negative to VSS. Yeah.
What direction does the electricity flow? Does it go through the resistor to the LED or the other way around?
So that's a great question. And that's actually, so the question is, which way does the electricity flow? Does it flow kind of starting here and going around that way? Or does it flow down here, starting there, and go around that way? Well, it turns out you can think about it both ways. So, and they have different names. So, this actually goes way back to the founding of, the discovery of electricity. When Benjamin Franklin was first looking at some curious phenomena that he noticed, he was playing around with electricity, and he said, okay, well, the electricity has to be going from the positive side to the negative side. So there was a convention that electricity flows from the positive side of a battery to the negative side. And so we call this conventional flow. So you can think about it that way. Later on, so Franklin came up with this idea, and people started using it, and it was very widespread. Later on, people did some more experiments, and they found out that what electricity is, it's the movement of electrons, and they found out that the electrons are actually going from the negative side to the positive side. So people said, hey, this is what's actually happening, we should draw it like that. So that is called electron flow. Okay? So you can think of these electrons, these negative charges, flowing from the negative side of the battery to the positive side, or you could think about positive charges flowing from the positive side down to the negative side of the battery.
So they're both flowing at the same time.
So they're both equally valid ways of thinking about it. It's sort of like if you dumped a bunch of water out of a bottle, you could think about the water flowing out of the bottle, or you could think about air flowing into the bottle. It's sort of...
So it's like two different sides of the flow.
Yeah, exactly.
Just kind of thinking about it. If you think about a conventional flow way, then is that, trying to think, if it's conventional flow, then we technically, you still need the resistor, right?
Yeah,
So-
yeah. You still need to build the circuit in the same way. Nothing about the circuit actually changes. It's just a different way of imagining it. Yeah.
So that's interesting because in my head, looking at it from here, like if it went from positive to negative, it would go straight to the LED and blow the thing up.
Yeah. So, so these are great questions. These are things I usually address a little bit later on, but I'm glad you guys are thinking about this. So I'll take a minute and talk about that. A lot of times when we talk about electricity flowing, we can think about it kind of like a fluid, like water or something like that. So, so you can think about electricity flowing through this circuit being kind of like water flowing through a hose or a pipe. And the resistor makes it hard for the electricity to flow. So that's kind of like a kink in the hose. Or so you're thinking about it, and it seems like the electricity is coming right out of here, and it's hitting the component right away, so it should be hitting it with full force and damaging it. But what's actually happening is that the thing that might hurt this component is the amount of electricity that's flowing through it. And so if you've got a kink in the hose before the component, that would surely slow down the electricity or limit the amount of electricity going through it. But if you had a kink in the hose after that, it would still limit the amount of water that was coming through that hose, right? So that's what's going on. This is like a kink in the hose. It's just, it doesn't really matter whether you put it after or before. It limits it in both cases. Yeah?
Is there a rule that you have to place positive on left or right, or you can use it whatever?
You can build it however you want. These diagrams just show the connections that we have to make. So typically we try and draw the diagrams in a a way that's easy to understand and nice to look at. But the diagram would be equivalent if I drew it like this, where I had the power supply upside down, and then it was connected to an LED over here, and then the resistor was down here. All the connections are the same. The positive side of the battery, and I'm sorry, the marker just ran out on me. The positive side of the battery is still connected to the anode of the LED, cathode is still connected to the resistor, and that's still connected to the negative side. So all the connections are the same. So these two diagrams are equivalent.
There is no code about distance, putting all the parts together. So
Right, in terms of diagrams, you could have them bunched way together if you wanted to save space, or you could have them move far apart if you wanted to add lots of annotations and things like that. The distance between components in a diagram doesn't indicate anything physically.
okay, so it doesn't make any explosion, something like that.
So if you're talking about actually physically building the circuit, if you put the components right next to each other, there's a possibility that you could bump them and they could touch each other, which might make connections that you don't want. Or there's a possibility that they could, if you had really high voltages, you could get a spark between them. So physically, when you build things, you want to leave a little bit of space between them. But in terms of the diagram, the actual distance on the diagram doesn't indicate physical space in real life. Is that what you're asking?
I'm sorry.
No, I'm glad you guys are asking questions. No, I'm glad. I'm very glad that you're asking questions. Because yeah, like I said, if you have these questions, I bet other people have them too, and I'm happy to go into those things. Yeah.
So what's the difference between an anode and a cathode? Like you touched on it briefly, I just want to know what purpose it will serve, what differentiates them.
Right. So if you hook the positive side of the voltage to the anode and the negative side to the cathode, then electricity will flow through the diode. If you hook it backwards, then the diode blocks the electricity and nothing flows. So, other questions about that? Yeah.
If it was flowing like electron flow
Uh-huh.
and the diode was placed the direction it is, it would still run? Or-
Yes.
Okay.
Yeah, exactly.
Because I thought the diode stopped electricity from flowing in one. Well,
Right.
you'll probably talk about that tomorrow.
Well, right. So that's one of the confusing things, right? So, so the diode looks kind of like an arrow pointed in that direction. So when you're thinking about conventional flow, it kind of makes sense that the electricity can flow through the diode in that direction, right?
Yeah.
So when you're talking about conventional flow, the electricity only flows through the diode in that direction. If you're talking about electron flow, the electricity still only flows through a diode in one direction, but it turns out that with electron flow, it flows through, the electrons flow that way. So the positive charges flow that way, the electrons flow that way.
Oh.
So yeah, these are great questions. I'm glad you guys are thinking about them. I'm concerned that I'm getting a little bit into too much detail right now. So if all this stuff is going over your head, don't worry about that at all. This is much more detail than we need for today. I'm just trying to address some of the questions as they come up. So other questions about this? Okay. I'm really glad that you guys are thinking about this stuff because these are great questions, and I just don't want to overwhelm you with too much information all at once. Okay. All right. So we made our first circuit. We made the LED turn on, and that is super cool. But it just kind of sits there, and it's on, and it doesn't really do much. It'd be even cooler if we could make it blink, right? Well, turns out we can do that, but all we need to do is a little bit of programming, okay? So we're going to look at how we can actually program these boards as well. Okay, so this is something called the basic stamp editor. This allows us to actually make our own program. Okay?
What was it called? Basics?
Basic stamp editor. Yeah. So when we make this program, and we run this program on our board, and we make a slight change to the way that our board is set up. Now our LED starts to blink. Okay? So let's see first what change we made to the board, and then, or to the circuit, and then see how the program actually works. Okay? All right, so the change that we made is that instead of just having the power, everything connected to a power supply that's always on, now we have one side that's connected to, this side is still connected to VDD, and this side is connected to something called pin 14, okay? And this is the only change that we have to make in our circuit. So let's take a look at this program and see what's going on. See how it allows us to make this LED blink. So first of all, we say, the first command I want to look at is this one. It's high 14. Okay? And high 14, have we seen the number 14 before? If we look over there, we've connected something to pin 14. Okay? So high 14 means that we're going to turn the electricity on pin 14. And we've got something that says pause 500. What would a pause command do? Yeah, it would make the program wait, and then you'll notice that there are these green this green writing off to the right hand side. Anything in green is called a comment. That's something that doesn't actually affect the program, but it's a note to you to remind you of what's going on. So this says when we have pause 500, that's a 1/2 second delay. Okay? So pause 500 means we're going to wait for 1/2 second. Now we say low 14. Well, high 14 turned the electricity on, so what do you think low 14 does? Turns it off, exactly. And then the note confirms that. It says turn LED connected to pin 14 off. And then another pause. Okay? So we're turning the LED on, we're waiting, we're turning it off, and we're waiting. Right? That looks like a blink to me, right? Turn on, wait, turn off, and then yeah.
So you have that device connected to the computer?
Good question. It's not connected to the computer right now.
So you have to do it manually?
Well, I'm not pushing anything. I'm just holding it. So what happens? That's a great question, though. How is the computer, affecting this thing over here when it's not connected? What happens is that there's actually a little computer on this board. This little rectangle down here is a tiny computer on this board, and what happens is that we write the program on this computer, and then we do connect it with a cable. We connect the big computer to the little tiny computer. We send the program from this big computer over to the little one, and then we can disconnect them, and the program still stays on this little one, and it keeps running, even after the two things are disconnected. Does that make sense?
And can you save the settings or?
Yeah. So they're saved. So even if I turn this off, even if I unplug the power, the next time I turn it back on, it still runs the same program.
You
Yeah.
have remote control?
Yeah, it's pretty cool. Did you?
I was just gonna clarify, but,
Yeah.
So in that case, that means it would have to have a data bank to remember it.
Yeah, it has onboard memory. It's one of these little chips. I'm not sure exactly which one, but it's one of these little chips on this this controller unit here. Yeah.
So I thought the resistor before was connected to PSS. So
You're right. I'm sorry. I wrote that incorrectly. Thank you.
By a way to do that, they have to have software?
Yes, you need to have the software on the computer in order to send the program over. Fortunately, the software is free, and you can download it off the internet. So, yep.
If you were to change the pause to 1,000,
Yeah.
making the increments before you make it a whole second.
Well, let's see what happens. This is one of the really cool things about this programming. You can make these changes and see. So I highly encourage you guys to experiment with this stuff in the lab and try stuff out and see what happens. So I've changed the program, and now I need to send it over to my basic stamp. So you need to have three things in order to send the program over. You need to have the battery connected. You need to have the power turned on. So let me pull this up for a second. To send over the program, you need to have the battery cable plugged in, which we have. You need to have the board turned on, so that means the switch has to be in position 1 or 2. And then you have to have this serial cable connected. So every computer in the lab is going to have one of these serial cables. You need to connect this serial cable to the port down here. So you need to do those three things before you send over the program. Battery turned on and serial cable. Once you have all of those things connected, then you can send over the program with this little play button on the top of the screen. So we click that, and it sends over the program. And now, you can see that, like you thought, it blinks slower. It takes longer, it waits for a longer time while it's on, and then it waits for a longer time while it's off. Okay. So what do you think would happen if we made this a smaller number? Yeah, so let's try that. We'll make it 100 instead of 1,000. Again, we'll make sure the battery's plugged in, the power's turned on, and the cable is connected. And we'll send this over. And we can see, sure enough, it's blinking really fast. Okay, so you can make these changes and see how it affects your program almost instantaneously. So I highly recommend that you play around with these things and see what's going on. Yeah.
Is that pin something that we connect into the breadboard, or is it just through the software?
Yeah, so that's a great question. Let me show you that.
Quick question about the little dot. Is the programming attached to which position power is in? So is this program stored on position 1?
Good question. Right, so I said that there are positions 0, 1, and 2 for the power switch. What happens is that 0 is off, 1 is mostly on, everything is on except for the motors. And then 2 is everything and the motors on. Okay, so you guys are not gonna, we don't need to worry about 1 and 2, the difference between 1 and 2 right now, because we're not playing with the motors. It'll be more important in a couple of classes when we actually hook the motors up.
So you can't do multiple programs, save it on the bot, just one at a time.
Right, just one at a time. Yeah. All right, and then Phil asked about the change that we actually made to the board itself and how we connected the LED differently. So before, remember, the anode of the LED was connected to VDD. So before, the anode was connected to one of these holes up here. Now the anode has been moved over to this hole right there. So I don't know if you guys can see it in the back, but there's this label that says P14 right next to that hole. So that means that this is the hole for pin 14. So anytime we make a program and we turn pin 14 on, that's going to make a high voltage here. And when we turn pin 14 off, that's going to make a low voltage there. Okay, so that's the difference. So questions about that? Yeah?
So the VDD is the constant power source, and then if we connect it to any of those pins, we can change it with the basic state editor.
That's exactly right. Exactly. Couldn't have said it better myself. Yep. Other questions? Okay. Cool. So we've covered pretty much everything that you're going to be. Okay. So let me back up for just a second. So we made the LED blink on and off. Right now it's just going on and off constantly. Maybe we would want it to go on and off a certain number of times, right? So first of all, let's look at how we make it go on and off constantly. We talked about turning the LED on, waiting, and then turning it off. And that's enough for one blink, right? Turn it on, wait, turn it off, and wait. So that creates one blink, but we want it to keep blinking and blinking and blinking, right? So in order to do that, we need to make it repeat. We need to take that pattern and make it repeat over and over again, right? So the way that we do that is with something called a loop. So if we want to make it happen over and over again, we use something called a do loop. Basically, we say do at the beginning, and then loop at the end. And the comments help you out. Up here at the beginning, it says the continuous loop start, and then down here at the end, it says continuous loop return. Right? So we're making the LED blink continuously. So that's how this program works. We might want to have a program that blinks only a set number of times. Okay? So we can open up this other example program that is called LED on-off 10 times. Okay? And you can see here, we've still got the high 14, pause, low 14, pause. So this is just the same as we had in the previous program. So that's still there, that's still going to make it blink on and off. The difference is that we use a different kind of loop here. Instead of using a do loop that runs forever, this one uses a for next loop. And it has this line up here, 1 to 10. So that tells it that it's going to run 10 times. Okay? So let's plug this in and run it and see what happens. So let me pull this up on the screen here. All right. So when I run this, watch the LED and see how it blinks. Okay? There's also this little box here, and it's counting how many times the LED is blinked. You can see the LED blinking at the same time. So it gets up to 10, the LED stops blinking, so it blinks 10 times and then it stops. Okay? So what do you think would happen if I changed this number to 5? Yeah, blink 5 times. So let's try that. 1, 2, 3, 4, 5. And then it stops after that. Okay, so this controls how many times the LED blinks. Okay. So that's how this program works. So let's take a look at the instructions for the lab for just a second so that you guys know what you're going to be working with. So the first part of the lab tells you a little bit about resistors. It tells you a little bit about what the color codes mean, but you don't have to worry about that. We're going to go into that in more detail later on. It gives you some introductory instructions. Then it shows you how to start hooking up these circuits. Okay? So on the left-hand side of the book, it shows you a circuit diagram. So this is like the diagram, the first diagram that I drew on the board. One side of the resistor is connected to VDD, then it's going to the LED, and then the other side of the LED is going to VSS. So this is a circuit diagram, and then it shows you how to make that circuit on the breadboard. Okay? So if you didn't remember exactly how breadboards work or stuff like that, don't worry about it. You just make it the way it's shown in the book here, and it should work for you. Okay? Remember when you're hooking up the LED, so remember to look for which side is the anode and which side is the cathode. If you plug it in backwards, it's not going to hurt anything, but it's just not going to work for you. Okay? So this is the first circuit. What should happen to the LED in this case? Is the electricity going to flow through it? Yeah, the electricity is going to flow through it here. So is it going to turn on or not? Yeah, it'll turn on. So then, this is the next circuit. With this one, it's kind of funny. They've got both sides of the circuit hooked to VSS. So here, there's not really any pressure pushing the electricity to flow through this circuit. So if you hook this circuit up just right, then you'll notice that absolutely nothing happens. Okay? So if you hook this up, this just shows you that the LED stays off when you hook it up like this. Okay? And then this is the third type of circuit that we built, where we actually hooked the resistor up to, or we hooked one side of the circuit up to the pin, and then the other side of the circuit to VSS, and we caused the LED to blink. Okay? So you guys are going to build each of those circuits, see how they work. At the very end, you can try to actually hook up two different LEDs at the same time. So this diagram shows you exactly how to do that, and you can run that. And then finally at the end it says experimentation is encouraged. So you guys are highly encouraged to try stuff out, like you were mentioning, changing around the times that things are on, playing with anything that you wonder about. You can try different color LEDs, stuff like that. That's totally fine. When you first get to the lab, you're gonna sit down on a bench, and you probably sit down with another person, and that person is gonna be your lab partner, okay? So one of you will go to the back and get a box of parts. It'll have the circuit board, it'll have some LEDs in there, some resistors in there, and that box is what you're going to be using for the next 3 or 4 days. You're going to take inventory of that box. On the inside cover of that box, there's going to be a list of all of the parts that should be in your box. So you're going to go through that list to make sure that you have everything that you need. And then when you're all good, you can actually start doing the lab for today. You need to write your name and your lab partner's name on the little piece of masking tape that's on the edge of that box, so that you know that you're using the same box next time. You'll get a battery from the back as well, and then you'll be you'll be all set. You can start doing the lab. The last thing I wanted to mention was where to actually find these files that I talked about in class. So you'll go, to get the actual programs, you're going to go to this drive, the instructor files drive. There's this folder called ET302. And then under lecture 1, L01, this is where you'll find the programs that you need. So there will be the LED on-off. That's the first one that just blinks continuously. And then the LED on-off 10 times is the one that blinks on and off 10 times. So any questions about that? All right, then let me take attendance, and then you'll be free to go. I know that we covered a lot of material today. Really, if you're feeling kind of overwhelmed, I apologize for that, but don't worry. We're going to go into all of this. We're going to cover it again and again and again. You're going to have lots of practice with this. So this was just a very brief introduction, and we're going to have lots more time to learn this stuff. Miguel Antelou. Here. Nathan Bolsover. Jessica Brown. Tegan Scott Brown. Here. Stephen Boycock. Here. Vitaly Dribnikov. Nathaniel Urey. Here. Jay Fleury. Here. Bobby Garrett. Bobby. Maria Guzman. Here. Ronisha Harris. Philip Hess. Here. Jason Jones. Here. Nathaniel Kirshner. Here. Sunil Kumar. Sunil. Barbara Lamb. Here. Raymond Miller. Here. Leslie Ngoya. Here. William Nguyen. Here. Sharif Newell. Here. James Powers. James. Selena Thomas. Here. John Tuminelli. Here. Austin Van. Here. Ann Veerkamp. Here. Jacob Wegat. Here. Tom Yang. Here. All right. Thanks, guys. Oh, Yep, yeah, we're all going to go with the lab. Yes. Yeah.
Does it matter what size or is it going to do it?
It does not matter. So,
But I noticed in the diagram it's going to do
right, yeah, so you could have had a straight wire here and the resistor up there. Yeah, as long as it's somewhere in the shape, yes. Yeah, I'll take those over, and if people don't have the lab books yet, I'll hand those out.